And here we are. Okay, so I'm recording. Let's share the content. I'm going to share the whole screen. Kaboom. And so there we go. That's what I like to see. Okay, so Facebook newsfeed, where we left off last time. These ACID properties. So when you have a database, a relational database, you want to make sure that there's only one correct answer in the database. Even if there are multiple replicas of the data, you want to make sure that whichever one of them you read from, it's going to be correct. So the way that happens is, again, through what's called ACID properties. ACID stands for ACID, Atomicity, Consistency, Isolation, and Durability. So we'll go through these quickly. So suppose you're changing your Facebook relationship status to it's complicated. Well, with atomicity, that first means a group of related database actions is atomic. Either they all happen or none of them do. They all succeed or they all fail. So this your relationship status is going to be stored in multiple places in Facebook's database, right? It's going to have a triple copy, probably, same as anything. So when you set this, right, when you make this status change, those replicas have to be updated as well. Well, if something goes wrong, if a piece of hardware isn't currently available for whatever reason and the request times out, you don't want to end up in the situation where one of them shows your old status and two of them show your current status, right? That would be an inconsistency. So instead, it says, sorry, we couldn't update all of them, thus it's all going to fail. And the system will spin its wheels for a while until the hardware times out, and then it'll say, sorry, we were unable to complete this request. Please try again in a few moments. That way you make sure that all the replicas are the same. They're either all current or, the attempt failed and they're all old ones. Consistency just means that any actions that happen in the database basically get processed in sequence and they follow whatever rules exist in the database. So, for example, suppose you unfriend someone prior to making that status change. Well, that unfriend shouldn't see the status change, right? But if the actions aren't processed in sequence, right, if the status change gets processed before the unfriending happens, right? So I draw a little picture in Paint. We have something that happens like this. If the sequence is friend and then, I don't know what happened there, and then attempt update, if what happens is we start, right, the start happens, then the start happens over here, but then maybe the next thing that happened, this thing's finished, finished and done, and then only later is this finished and done. For whatever reason, the defriending takes longer. It's possible that in that interval, right, if your friend looks at this, they could say, hey, I can see that, right? Your unfriend could see this state, and that's because you didn't have consistency, right? Your actions weren't processed sequentially. Okay, next one, isolation. So isolation means no database operations are going to affect others directly. Basically, they're all isolated from each other. So any operation is going to work the same regardless of what's going on in the system. And in practice, this means multiple actions having access to the same data. Okay, so what this means, for example, I'll give an example of isolation. Imagine if you have three replicas, right? Replica 1, replica 2, and replica 3. Okay? Suppose you have some friend, right? So your unfriend. While this action is going on, while the changing action, okay, so the action number 1 is defriend. Action number 2, status update. Okay? Let's keep it a little simpler. Let's just say this person is a friend, actually. We'll do this. This is a friend. Okay? and there's an action of a status update. Well, they might take longer on one of these. Suppose this one happens right away. I'll box it in green. And this one happens right away, but this one, for whatever reason, takes longer. Okay? Takes longer to update. Update. And it so happens that that's the one this friend looks at. Okay, well, the problem is, general problem, if an outsider, right, if an outsider can see into a database operation while it's in progress, they would see unpredictable data, right? If you have these three replicas, and even though eventually you're going to do them atomically, you're going to change all three or none at all, if you process where these two have changed, and then this friend comes in and happens to look at the third one before the update is complete, they're going to see wrong data. More generally, if anybody can look in at any of these three replicas while the operation is going on, while the update is going on, then what they'll actually see as a result will be unpredictable. This is a problem. This is what happens when you don't have isolation. So what you want to have happen, the solution, no one can see a database operation in an intermediate state, right? They only see the start or the end. So either all replicas updated or no replicas updated. And that way, at least you know what's going to happen. Okay. Last one, durability. Durability is pretty straightforward. It just means the database is robust against failures. That means once you make an update to the system, it's in there permanently. Even if there's some hardware failure and they have to restore some part of the system, that change is not going to be lost. Once it happens, it's permanent, right? So any database operation is durable. Even in case of hardware failures, you're going to be able to restore the system to a state where that operation had already gone through. Okay, so if you have those four things, atomicity, consistency, isolation, and durability, basically you know that any database operation that happens, it's going to be correct, it's going to be processed correctly and in sequence, it's not going to be lost after something goes wrong, and any user of the system is only going to see one answer, right? Because of atomicity, either everything happens or none of it does. Because of isolation, you only see what's happened after the operation is finished. You're not in some intermediate state where some of the replicas show one value and others show a different value. Okay, the downside of this, following these ACID properties in a database at scale will really slow things down. For example, if you have a system where you have only a couple replicas of popular data and a lot of people are accessing it over and over, imagine, for example, if there's some popular post by some notable and tens of thousands of people are commenting on it. Well, guess what? It's going to really suck if every one of those people has to wait for the other operations for all those other people to clear through, right? Anytime anybody makes a change to that, it's going to have to be echoed to every replica. It's going to have to be processed completely before the next person can do it. And when you multiply that by the number of things going on in Facebook at any given moment, yeah, it can really slow things down. Okay, again, it can also cause other problems like deadlock. Sometimes you'll have one operation that's waiting on another one to finish. For example, anytime you have two people posting on their profile, right on somebody's profile, number one, it creates an entry in that person's profile on Facebook, but it also creates an entry in your activity log. And so if two people are simultaneously trying to post on other people's profiles, that's going to create kind of a deadlock where the processes are going to block each other. You can't post the update to the activity log until you finish doing the profile, but that person's activity log is going to be held frozen until he's able to process his action on your profile page. So things like this can happen quite often. Well, if deadlock's a little confusing, that's okay. We'll talk about it more. But there's a lot of places where you can think about you don't really need ACID. You can cut some corners. For example, does it really matter that much if a user's post on one server isn't immediately echoed to everyone else's, right? So if I post something, sure, maybe there's people in Chicago that are interested, but it's probably, I don't have that many friends, overseas. I know a few people in Europe, a few people other parts of the world. But if it doesn't instantly get echoed right there, it's not that big of a deal. Likewise, if I have pools of people, some people see everyone around here that's liked a photo, other people involved with different data centers, they might see a slightly different mix for a while. I mean, Facebook will catch up, but if there's some slight temporary inconsistency, it just doesn't matter that much. So Facebook, in many cases, has chosen a policy of what's called eventual consistency. So eventually, the system will be consistent. All the replicas at all the data centers, they will eventually hold the same data, but there might be some different information until then, right? So like I said, one copy of a post at one data center might show a different Sykes than another for a little while. Okay, so Facebook uses a different database model in many cases that prioritizes speed over perfect accuracy. So again, this can result in non-critical inconsistencies. One model that's very popular for this sort of thing is called NoSQL. So NoSQL isn't a single database design, it's actually a set of database designs. And the main goals on it, making it flexible so it's easy to add or remove data fields, or have variable data sizes or data structures, and break it off into break off a database into many different devices instead of having it on one machine. So let me give an example. And Facebook has done a bunch of different ones over the years. So that's just a quick list, right? I mean, we talked about Haystack, but there have been many others. So we'll explain why this is an issue. We haven't really talked about this, but we'll take a few slides and we'll explain why this is an issue. First thing, a relational database can process queries very quickly. Reason number one, the fields in each record are known, right? Every record in a table has the same fields. So if you're writing a query around a table, you can say, yeah, I know that field is going to be there. Solves the problem. Number two, because the fields are uniform, for example, a short text field would have the same length for all records, right? The system knows exactly where to look. So when you're writing the code that checks these things, you could say, look here, look here, look here, look here, look here. Okay, so let me give you an example. Suppose every record in a table has exactly 1,000 bytes of data, okay? And suppose the relevant field in a query always starts at the 100th byte in the record. Okay, so then I know record 1 dot field is going to be at memory address 100, right? It's going to be at the 100th byte. The second record, the field is going to be at 1,000, right? Offset for the record plus 100. The next record's same field is going to be at an offset of 2,000 plus 100, and so on. So you don't need to actually look up the location, just instead you can calculate the memory address to find it. And this can save a lot of time on big tables. Okay, so relational databases, they can process tables very quickly because not only do they know that stuff is there, they know that within a record, they know exactly where that field is going to be. And so they can just check the particular memory addresses and find everything. On the other hand, we'll talk about NoSQL tables in a minute. For NoSQL tables, not necessarily true. Okay, so that's the trade-off. Let's talk about NoSQL tables for a minute. So the essential ideas for a key value database. Well, what is a key value database? Essentially, you have a table that's a list of keys that individually identify the objects, and then the value could be any sort of data structure. So essentially what you're having here, we'll give an example, key value store. Okay, just like in a relational database, you have a key for every record. And that's going to uniquely identify each record in a table. Okay? But a relational database, every record in a table has the same uniform structure. In a key value store, every record could have a unique structure. So if you want to look at it, essentially a table containing a keyed list of tables, right? So every record in a key value store could be entirely have its own unique structure. So number one, I call it a KV store, key value store. You don't know if a particular record even has the field, right? If you're looking for it, if you're writing a query. Number two, you wouldn't know where the field began inside the record, right? Within the record. So all those details need to be looked up separately for each record. And that can really slow things down. So key value stores, if all you're doing, if you're just looking for an item in the table, it's fine. For example, a Facebook photo, right? Facebook stacks up all these photos. You want to find a particular photo, great, go look it up from the list. There it is, you get it. It's not going to take a lot of time. But if you want to do any sort of complex query based on data fields in records, it could be very slow. Okay, so that's one thing. I'm going to box that up as a particular note. Number two, let's make another box. I'll write that up in a second. Key value stores use storage space much more efficiently. Okay? Any relational database has to use same size fields, which may be wildly inappropriate for variable size data like images or videos or even documents. Okay? So that's another thing. That's a whole separate thing. So with a key value store, you can just stack on the data one object after another, right? One record after another, because you don't have to worry about structure. So for an image, if you have a small image followed by a big image, followed by a small image, followed by a big image, fine, you just pack them into the storage media as closely as you can, right? With a relational database, because we want every record to be the same size, we force that uniform structure. you have to allow for the biggest possible item of that size. For example, if you're going to allow a photo to be 10 megs, then you have to allow 10 megs for every record. And that could, again, eat up a lot of space. Most of your photos aren't anything like that large. Okay, last thing. Okay, whoop. Because KV stores don't impose table structure, right? Basically, every record can have the same, can have a unique format. It's no problem to have multiple, it's no problem to change fields. They're already set up where every table can have its own, every record can have its own unique structure. Thus, if you change a field within a structure, that doesn't really cause a problem. However, relational databases are generally carefully calibrated to run well, right? To run fast. And changing a field can throw all that off, requiring recalibration, okay? Which can be a colossal pain in the ass. You don't really want to do it unless you have to. Now, if we're doing some simple stuff in Access, where we have like 100 records, and I change a database field, yeah, that's pretty trivial. But if you have some gigantic monster database where all the tables are spread out over hundreds or thousands or even more hard drives, then yeah, changing a field in that can really throw off your whole system. And what used to maybe run great now suddenly becomes almost unusable because it's so slow. So you have to do kind of a whole re-engineering, whole retuning process. So you don't want to do that. So those are the three trade-offs. Number one, for these NoSQL methods, especially the key value store, it can't handle complex queries very well. However, it does use storage space more efficiently, and it is much easier, much less painful to change fields. If you want to change the structure of a record, it's easy to do. So that's the trade-off. You have to take simpler queries, but more efficient use of space and more flexible. Okay, so that's what I mean here. In particular, when I say no table joins, in a NoSQL database, like a key value store, it's very, very slow to do queries across tables. Relational databases, as we'll see in the next lab exercise, are specifically designed to support queries involving multiple tables. With key value stores, it doesn't work well at all. It's going to be very slow because anytime you're scanning through a table, you have to check and see if those fields you're looking for are even there. You're not going to know, and you don't know where they're going to be. You can run those queries. They're just going to be really slow. You don't want to run them. Okay. Now, where do key value stores make the most sense? Well, number one, if you have objects that don't have a definite form, like if you're storing web pages or if you're storing some sort documents of user history, yeah, there's not a single form for that, right? Some web pages could be very short and simple. Some could be tremendously long. Same for Facebook user history. So you have varying data sizes. Relational database is not necessarily going to be a great fit. If you have very large objects that require horizontal database scaling. So one of the things I mentioned is if you have a relational database, it can work great. You can run queries in it as long as those queries are confined to a single machine and you're operating at, RAM speed. However, if you have a table that's so big that it's split across multiple machines, then queries you do, especially if you're doing like cross checks of tables where you're seeing if a record in one table exists in another, then those operations aren't going to happen at RAM speed. They're going to happen at, network speed, which is a lot slower, or worst case, maybe even at hard drive speed, tremendously slower. So if you have very large objects that require horizontal database scaling, basically if they're going to be spread out over multiple storage systems, storage devices, that's going to be terrible for running complex queries like that. So again, key value pairs, you're going to say, well, we can't run these complex queries anyway. Let's use at least efficient storage space. So if you're having like vast storage of videos or images, you're not going to store all that on a single machine, so a key value store might be a good option. Last, if you have unrelated data used together, for example, if your records themselves don't have a consistent form. So if you have a security application that gets log files and cached application data, that's not going to be the same for every application. Different applications will generate log data in different formats. They'll have different kinds of application data. You're not going to be able to store it in one single sensible system. So it does make sense. You might have records that indicate we're talking about this application, and then you can identify, oh, well, that application has this kind of data, and you can have that common structure at least. But it doesn't make sense to build a whole table around all the applications you might use because they all have different data. So a common structure, right, with all the records having the same fields isn't really appropriate. Okay. Last thing, market status. So this is a few years old, but what you can see looking at it, relational data, this green at the bottom, it's by far the large chunk. Other things are this black bar in the middle, Hadoop and other NoSQL platforms. Yeah, they're gaining. They've definitely gotten bigger over the last 5 years. And other non-relational types, they've shrunk. So you can see that the NoSQL is taking a huge share of everything that's not relational data. But it's worth mentioning this. Number one, this is the database market. These are products and services that are sold to other companies. For example, Oracle, which is very big in the relational database world, this is what they're selling. So all the other things, all the NoSQL databases that your big companies like Facebook, Amazon, YouTube, Google, all those non-relational ones that they're building in-house, they're not reflected in this. Okay, and so it's entirely possible that these other non-relational or partially relational ones are a substantially bigger share. But, since they're internal, nobody's really put a price tag on them. All right, so key takeaway, NoSQL is a small but growing fraction of the paid database market, but of course those numbers you see don't reflect proprietary systems or open source systems that nobody pays for. Now, what we see going forward as big data is getting bigger, and it's going to keep getting bigger, NoSQL systems, or at least semi-relational systems, they're going to be the prime beneficiaries. These systems, the amount of data they're storing is going to get so large that in most cases a pure relational approach will not work very well. Okay, it does look like for the next several years relational databases will remain the dominant product category, but these other ones, these other NoSQL systems are going to keep on getting bigger behind the scenes, right? Google keeps getting bigger, Amazon, Facebook, YouTube, all of them, they're getting bigger. Okay, and that's it. That's it. For any of you that are still here, I do thank you for your attention. I'm going to stop the recording, stop the sharing, stop